Well, welcome to this programming tip. In this week's practice project, we took two CSV files, and our task is to take those two files and join the resulting tables based on a shared field. In this particular case, it was both tables had FIPS code, and we were trying to join those two tables based on a common FIPS code. Now, this problem of joining two tables together based on a shared field is actually a very common one. This comes up in databases all the time. And companies like Oracle have literally spent hundreds of thousands of man hours on optimizing their code to do this operation because it's done so often and on such large data sets. In the last video, we talked a little bit about the efficiency of list operations and dictionary operations. And what we're going to do is we're going to look at two different approaches to joining two CSV files. One that's going to use a pair of lists, and the second one is going to use a list and a dictionary. And we'll see that the efficiency of the underlying operations in Python is going to influence which one we choose. Let's go to it. Okay, before we look at some Python code, let's look at the two data sets that we're trying to join. So here I've opened one of the CSV files in my spreadsheet. This is the one that has the cancer risk. And you can notice in this table, there's state and there's county name, and then there's this column, which is the FIPS code, which is kind of a unique identifier for a particular county. We have a population, we have a cancer risk. So this has basically cancer risk for all the counties in the United States. So for example, New York City's county is 3061. Now, in a previous week, we've gone through and we've taken a map of the United States and we've kind of computed the center of each county in terms of the coordinates of that map, and we wrote it out in a CSV file. So if we kind of throw that up here, you can see here that we have things with FIPS codes, horizontal coordinate, vertical coordinate. And what I've located here is somewhere down this table, here's the county center in terms of this map for New York City. So what we'd like to do is write a program that takes these two tables and takes rows that share a common FIPS code and kind of joins all the remaining information. So we join the two tables together to make a single table. And so that's what this join operation is going to do. And we're going to look at how we can do this in Python. Okay, let's talk about two different approaches to joining two CSV files. So I've provided you with some Python code here that's going to do two things. We're going to do a little benchmark. We're going to actually check actual running times in Python. And we're also going to do a little thinking and try to understand the efficiency of both approaches. So here I provided some code that reads in a CSV file. And here's the first function that we're going to look at. This function reads in the two CSV files and strips out just the column corresponding to the FIPS code. So we're not going to worry about the other data right now. And this first piece of code here in our testing code does the following. It reads in a table, strips out the FIPS code, stores them in a list. Reads in the second table, strips out the FIPS code, stores them in a list. And here's the critical piece of code that we want to look at right here. So what this code does is it iterates through the FIPS codes in the first list and then uses in to check if that code is in the second list. Okay, so it's going to go through the first set of codes, check to see if it's in the second list of codes. All right, now we'd like to do a little benchmarking. So what we're going to do is we're going to measure the running time for that. We're going to see how long it takes to do it. And so we can just do that in Python. There's a module called time, and there's a method called time in that, which tells us basically the start time when that command is executed. And so what we can do is we can compute what time it is before we execute this loop, and we can compute what time it is after we execute this loop, and then we can print out the result. Here's the second approach to it. We're going to take the second table, and what we're going to do is we're going to create a dictionary, and the dictionary is going to have a key corresponding to the various codes in the second table, and the value is not so important. We'll just put true in there. And what we're going to do is we're going to iterate through the first list, and then we're going to check to see if each of those FIPS codes is in the dictionary corresponding to the second table. Now, what I told you kind of in the last lecture was that checking membership in dictionaries is faster. So let's just run this and just run it on our two pieces of data and just see what happens. So we're going to hit run here. And what you can see is there's about 3,200 FIPS codes for both data sets. It checked for membership using a list, and it took about 1/10 of a second. We checked for it using a dictionary. It took 1/1000th of a second. Okay, that seems to be pretty nice. I mean, really, in reality, 1/10 of a second, that's not too bad, is it? So remember what we talked about when we wanted to measure efficiency. Benchmarking itself is maybe not so useful as to know, okay, we're running on 3,000 FIPS codes. What if we had 3 million FIPS codes? What would happen? Would the difference still be very, pretty small? Would it be less than maybe a second or something like that? The answer is I'm going to write a second piece of test code that's going to kind of abstract things out a little bit more. And we're going to check how these two methods change as the size of the lists varies. Okay, in the first part of this video, we saw that our Python code for joining two CSV tables was slightly faster when we used a list and a dictionary as opposed to two lists. Okay, one question that we should ask ourselves is, was that difference, is it going to stay the same as the size of those CSV tables gets bigger, or is it going to get worse as they get bigger? So what I'm going to do is I've written a second function here that's going to let me vary the amount of data that we're trying to manipulate. And we're going to look at how the running times of our algorithms increase as we increase the amount of data. So in this particular piece of code, test size is n. It's kind of something that controls the size of the data. We've initialized it to be 10,000. And the stri is going to be kind of a subset of the numbers from 0 to 10,000 we're going to work with. So test list is a list consisting of 0, 3, 6, 9, 12, all the way up to 10,000. And test dict is just a dictionary that just has those numbers as keys. And so we're going to run two pieces of code here. The first piece of code is going to iterate over the numbers in the range from 0 to test size, that's n, and it's going to check for each of those numbers if it's in the test list. And the test list is kind of size really n over 3. So if you think of that, we're doing something of size n over 3 n times, that's really kind of O of n squared. It's quadratic. All right, the second approach is we iterate over the numbers between 0 to test size, that's kind of n things, and we check to see if that number is in the test dictionary. And the critical thing here was that checking to see if something was in a dictionary took constant time. Remember, list, it took linear time. So it's constant time. So the total time from this should roughly be O of n. It should be linear. So again, we'd expect it to be faster. So let's run this and see what happens. And what you can see is that it runs faster for the list dictionary version than it does the list list version. In fact, substantially faster. Now let's try to confirm that these methods are quadratic for list list and linear for list dictionary. So here's a way to kind of empirically check that. Let's go through and just double the size of our data. We're going to go from 10,000 to 20,000, and we're going to run this. And what we'd expect the running time for list list to be about 2 seconds, the running time for list dictionary to be about, maybe a thousandth of a second. Let's check it. 2 seconds, about 1 millisecond. Looks pretty good. So what we've noticed here that things grow much faster when we're using list list, and that's consistent with the total time being quadratic. All right, one thing I want to point out is how much faster the list dictionary method is whenever we just stick to using lists and dictionaries. So I'm going to comment out the code that does list list because it's just going to get too slow too fast. Let's comment it out, and let's just start doing the final. Let's increase the size of the data set by factors of 10. Now, every time we increase it by a factor of 10, we'd expect this running time to roughly go up by a factor of 10. So when we run this now, we should see the running time should be about a hundredth of a second. So let's go through and do that. I'm going to make that 20,000. We're going to hit run. What we saw is, yeah, it's about a hundredth of a second. Okay, let's run it and change this to another factor of 10. We'd expect us to see about a tenth of a second. Yeah, pretty close. Okay, let's do it one more time. Let's run it again. Took around 2 seconds. So what you can see is this growth in running time is consistent with the algorithm being linear time. Now, hopefully this will kind of open your eyes to kind of a little bit of the importance of understanding algorithmic efficiency when you're writing code in any language, but especially in Python. So I really recommend that you spend a little bit of time looking at the time complexity page for Python and maybe going out and learning a little bit more about algorithms when you get the chance. Okay, I'll see you next week.